Our last presenter today is Francisco Chitty. Francisco is a PhD student at FIU with a focus on structural engineering. Florida slab beam bridge with ultra-high performance concrete joint connections.
Thank you very much, Dr. Bektas, for this brief introduction. So my name is Francisco. I'm the graduate research assistant for this project. My advisor is the principal investigator, Dr. David Garber, and the project manager for this project is Ms. Christina Freeman. The outline of this presentation, I will be covering the background of current or previous Florida slab beam superstructure system that has been built in the past. And later on, I will talk about the development of the Florida slab beam section, FSB, and how we are going to incorporate the joining material, UHPC, in the development of a new system. Objectives of the project will be discussed. Joint development in terms of geometry and rebar construction. The experimental program we are carrying out right now, the summary of some of the results we have had so far, and the update of the current research. So in the background part, Florida has developed several types of slab beam systems. Here are a few of them. The top left corner, we have one of the very first pre-stressed rectangular slab units back in 1955. And we can see here it has a 10-inch wide closure port, and forming was required underneath the system. When we go to the right, top right, pre-stressed keyed slab units, 1958. This particular section did not require forming underneath, so the casting place deck was easier to build, 4-inch casting place concrete topping. And it included transverse tie bars in sleeves. These were not post-tensioning. And if we go to the 1959, the bottom left corner, we have the sonovoids. This system was very popular in the 50s and the 60s, and it has voids to reduce the weight of the system. Transverse tie bars in sleeves were included, or transverse post-tensioning was used as well. Grouted shear key in the middle, and it had a 4-inch asphalt topping. It did not include the casting place concrete topping. Pre-stressed slab unit, PSU, back in 2008, optional PT was used for this type of system. It had a grouted shear key and a 6-inch casting place concrete topping. In terms of the performance of this system, some of them has performed good over the years. However, we have seen longitudinal reflective cracks. The picture doesn't show them, okay. But this system is losing the diaphragm behavior, so the beams might be acting independently. So that's why we can see this longitudinal reflective crack running all the way through the joint region. And then the most recent iteration of the FDOT slab beam system is the Florida slab beam, FSB, the one you see at the bottom. It's a precast, pre-stressed slab beam designed to act in composite action with the casting place deck. The width of the system, the width of the beams goes from 4 feet to 5 feet, and the thicknesses 12, 15, and 18 inches. So the current FSB system, it's a iteration or modification to the Minnesota slab beam system. Is called precast, composite slab span system. So one of the main differences is the joint region protruding steel rebars. In the Minnesota one, the rebars are overlapping between the slab system. In the Florida slab beam, they are not. But both of them include a cage that is placed in the joint region. So this video shows current construction of the FSB superstructure system. The beams are laid down side by side, leaving a clearance of 3/4 of an inch, more or less. Here, the protruding steel rebars are not shown, but you'll see the application of the cage I was mentioning before, all the way through the joint connection. This also includes a math, number 5 Reavers running all the way across through the superstructure system, which is the reinforcement of the casting place deck. After this is finished, the bridge can be open to traffic. These systems are designed to be applied to short span bridges in low annual traffic volumes. The background of the UHPC, this is the material we want to start using for this type of joints. It has some of the properties, compressive strength of 20 to 30 KSI, very high compressive strength, and also very high tensile cracking strength. So this higher tensile cracking strength is due to the fact that the material is using fiber reinforcement. In this case, it's a steel fiber reinforcement. Also higher modulus of elasticity. So the objective of the project, we are departing from the current FSB construction system. We want to implement a modification to the geometry of the slab beam to use UHPC in the longitudinal joint. Therefore, we're ending up with a new accelerated construction method. We're getting rid of the casting place deck. The only cast to be done on site will be the longitudinal joint. The way we started the development of this joint, we first did a parametric study to see the feasible span lengths the original system can achieve. So the top 2 images, the current design includes a 12-inch thickness, a slab beam, and plus 6 inches as a casting place deck. So we developed the parametric study using the bridge you see in the image, 2-lane bridge, very common for short span off-system bridges. And then we use also a modified section without the casting place deck, just the FSB section and the pour in the joint region. Because we had a decreased lever arm, the system without the casting place, we call it on top, reached a lesser span length, which was 55 feet. With the top, the casting place deck, we reached 61 feet. Therefore, we have to come up with a thicker section if we're not using the 6-inch casting place deck. If we're not using that, we have to come up with a thicker section so that we can compare it directly to the current FSB section. Some of the details we studied during the literature review. These are the most common UHPC joint connections, longitudinal connections for, in this case, are for slab beams and also precast panels. So you can see you have headed bars, you have hook bars, and also non-contact lap splice length. The reavers are not touching between each other, but there is a lap length. Also notice the shorter connection width goes to 6 inches to 8 inches as well. So we studied also thicker sections, which is this one, the box beam. It was used, this box beam section was modified to implement also UHPC. So the idea was to get rid of the transverse post tensioning and the grouted shear key. So the only pour will be the UHPC, and it'll guarantee enough diaphragm behavior for the whole system, for the whole superstructure system. So this is the geometry we are first using in our FSB section. So we have the original FSB section, and we incorporate that red line, which is the modified geometry. We can have additional strands as well. And then we're ending up with the modified FSB sections, which we called alternate 1. Also, we did another modification, or the FDOT engineers did another modification to the original FSB. They thickened the section of the FSB, taking advantage of the shorter development length the reavers can achieve using UHPC in the joint region. The only difference between these two is the bottom lip. You can see here. So this is the final joint details, the 3 joint details we are testing right now, currently testing. The top one is the alternate, and the bottom 2 ones are the option 2, option 3 that we call FDOT1 and FDOT2. So we use to develop these details, we use a publication by the Federal Highway Administration, which describes the use of UHPC in field cast connections for panels and slab beams. So the right top figure, you see how densely the Reavers are from the current FSB to the bottom right, which is just the non-contact lab splice length ensured for the Reavers. So we have 4 types. For the preliminary test specimen, we have 4 types of joint, the current FSB, which is 12 plus 6 inches thickness, the 2 FDOT, 1 and 2, and the alternate. All of those 3 are 18 inches in thickness. And we developed also a 12-inch set of joint details. The way we test them, we wanted to test them in Flexure, so we developed this testing scheme where we had the maximum width for the both FSBs, or the both modified FSBs, and we cast the joint region, and we only had 56 inches of longitudinal length. Therefore, we are having flexure in the transverse region of the system. The way we apply the load, we simulate a wheel path of an HL93 truck load, ASHTO, and it has a 20 by 10 inches wheel path. These are some pictures of the experimental testing. These are for the current FSB. We have the side view, bottom view, top view. All the specimens were heavily, we installed heavily sensors to monitor how the load is being propagated throughout the whole specimen. So we had concrete strain gauges, top and bottom. We had Reaver strain gauges to measure which rebar is engaged during the application of the load. And also we had crack displacement transducers to measure the opening between the 2 beams when the load is being applied. Also, I forgot to mention, the load is being applied next to the joint region so that we can ensure shear and bending moment at the joint region rather than just bending. Some of the videos we can see here, these are the 3 12 inches specimens and their failure loads. For example, the 12F1 top left, we had a failure load of 70 kips. The next one is 12F2, 98.1 kips, and the bottom one is the alternate. We had a 61 kips failure load. For the 18 inches, here we compare the control. This is the direct comparison we have for the control one. The control failed at a lower capacity. I will explain that later. You can see the 18 inches of the 18 inches specimen, 154 for the alternate, 149, almost 50 for the F1, and 170, which was the highest, the strongest one, F2, 18 F2. So these are the numerical and experimental modeling. Before doing the experimental testing, we ran some analysis, nonlinear finite element method, and so that we can have a ballpark value where these beams will fall at. So you can see the max 2 main columns, max force, and the displacement at the center of the specimen at the max force, right where the max force, where the specimen fell. So we have all the specimens. We compared the software analysis and the experimental test. So we can see here, this is the issue I was talking about, that we had a development failure that occurred before yielding of the Reavers, of the protruding Reavers. So the software predicted 153, and the experimental test got only 63.42, very low. But overall, you can see if you compare the other specimens, the comparison is, the failure loads are very similar. We did a very good approximation when we were analyzing in the software. For the F1, 149, for the F2, 169 and 170. Alternate, we even had higher capacity compared to the software. So what we're doing is comparing the experimental test of the new development geometries to the software analysis of the control FSB, which would have been the intended behavior for this type of specimen. So in the 12 inches, we got closer values as well compared to the experimental and the software analysis. And here, the difference in the lever arm, the location of the vertical location of this protruding rebar plays a major role. The difference between F1 and F2 was about an inch difference in lever arm distance. So you can see how much strength we can gain by lowering the rebar. This is a load deflection curves for all the 18-inch specimens, which are the direct comparison. So you see 2 lines per specimen, one dark and one light. You can see the blue, that bottom one was the FSB. We tested each section twice. And you can see here, for example, the yellow and the green one are the two F1 and F2 specimen, being the highest, the F1. However, if we pay attention to that red line, which was this detail, the alternate one, we can see a higher ductility achieved for this type of specimen. So preliminary recommendations we have so far, the experimental testing for the current FSB, this is the reason why the FSB failed sooner. We specify in our original joint design a 90 degrees bend, but we got that type of faulty bar bend in the FSB control joint. So this is a matter of construction. We specify the precaster, like you can have like threaded bars and then bend them. But this was the solution they implemented, but this did not ensure correct development length between the rebar and the control and the casting place deck. So we have to ensure proper bend detail during construction. Another thing, and this is, I think it's the most important one, it's the aggregate exposure or the aggregate finish in that joint region. So there are many types of ways to achieve the aggregate exposed finish. The Federal Highway Administration recommend ones, according to them, is the best one is to use a set retarding agent so that you can have that exposure of the aggregate, and it ensures a 1/4-inch roughness surface, which is the far left image, versus sandblasted. Although we specified that exposed aggregate on the left, we got the sandblasted, so we did not get that much bond between the UHPC and the regular concrete. So we observed some debonding between the UHPC and precast concrete, so this might be an issue in the future because water can enter between these two regions and cause damage to the bottom rebars, or even from below as well. So the set retarding agent is a very important thing to ensure when trying to develop this type of joint connections. So in summary, the joint strengths we got, these are all 18 inches results. The Pmax for all the beams developed versus the Pmax of the original FSB. We develop a higher, equal or higher capacity, which was the main goal of this project. So these were under monotonic loading. Now we're testing the two best performing in cyclic loading, which is the alternate, the top one to the left, and the middle one, the F1, which is 149.9 kips. I would like to acknowledge my advisor, Dr. David Garver, and also the project manager, Ms. Christina Freeman, and the rest of the team in the Florida Department of Transportation lab. Thank you for your support, and thank you for your attention.
I noticed in the example that you showed here, you tested for positive bending transversely. How do you handle negative bending and the tension stresses that can occur at the top? These are just flexure testing. We call it a small scale. Later on, we plan to test large scale, and that's another point we want to test in the future for this new type of girder. So we plan to incorporate another layer of rebars at the top. You saw just one. We use the simplest geometry we can achieve to test them, and then we are going to enhance the geometry as we come along.
how do you handle the writability on the slabs? Like I've seen some where they increase a sacrificial amount and then grind it at the end, or anything concerns with that?
There are two options being discussed right now for the writing surface. That's one, to thicken the cover of the slab beam, and might be used another option, which is use a membrane and then on top of the asphalt overlay. But we think the first one is the best application to ensure longer durability. Thank you very much for your attention.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.